Okay, welcome back everyone to another one of these tutorial videos on the theory of computation. So in this video, we'll be discussing the very interesting topic of P and NP. Okay. So in case you don't know, P and NP are two classes of decision problems. So these are classes of decision problems, or also of languages. But from now on, we're almost exclusively going to refer to them as decision problems. Just keep in mind that a decision problem can be sort of encoded as a language. How do you do this? You take all the yes instances of that decision problem, and that becomes the language corresponding to that decision problem, right? So just a quick reminder, if you have a decision problem P, decision problem Q, sorry, then the language corresponding to that decision problem is all of the instances where maybe the instances are sort of encoded in binary, right? So, X is in 0, 1 star, such that the answer to X um, such that X is an instance of Q represented in binary, and the answer to the decision problem Q of X is yes, right? So you collect all of the yes instances, you encode them in binary, you put those all in the language, and that's L sub Q, right? And so um, this is sort of always happening when we're talking about decision problems, because the really formal way of talking about decision problems is through languages. But really in practice, because we'll be doing manipulations on graphs at some point, then it will be easier to stick to just the graph representation of the input as an instance of the problem Q, for instance, right? But this is just to keep in mind as we talk about these two classes of decision problems, or like I just said, of languages. And so what is the difference between P and NP? So let me give you a definition for P, right? So a decision problem Q is in P if there exists a deterministic Turing machine which decides P in polynomial time. And when we say polynomial time, we mean with respect to the size of the input. Okay, so there's three very important key terms here. The first one is deterministic Turing machine, right? Something that we've already talked about in previous videos. The notion of deciding, something we've also talked about in the context of languages, but this transfers over to decision problems. Is in P if there exists, sorry, I'm just realizing which decides, so this should say Q, right? Q in polynomial time, and that's the third key word, right? Polynomial time. So given a binary representation of an instance of the problem Q, then the number of steps that the decision procedure or that the deterministic Turing machine should take, the number of sort of computational steps being the number of transitions it take, should be polynomial, should be a polynomial function of that input size, right? And so quickly, if we sketch that out, that means that we have a deterministic Turing machine M, such that if you give it an instance of the problem Q and the answer is no, then the deterministic Turing machine correctly says no. If the answer is instead yes, then the deterministic Turing machine M says yes, right? And it does this for any input, right? It either says yes or no, so that means that it decides, right? There's no infinite loop that occurs on any input, right? So that's why we're in the realm of decision procedure. It's doing this deterministically, which means that there's never any guessing in M. So recall what guessing looks like for Turing machines is, you have something like, I don't know, a loop here where if you're reading X, then you're writing X, you're moving right. But also if you're reading X, then you're writing X and you're moving right and you're going to another state, right? So this would be an example of non-determinism, and this does not occur in a deterministic Turing machine. And the last thing is that this occurs in polynomial time, right? So that means that if the size, so if the size of the instance of the problem Q that you're giving to the deterministic Turing machine is, let's say n, maybe n bits, n letters, whatever, then the number of computational steps, so i.e. really the number of transitions that M takes to decide I sub Q is polynomial in N, right? So it's N to some power K, right? So that's essentially what being in P is, right? So it's essentially, can you find, in layman's terms, really, for a computer scientist who doesn't know anything about Turing machines, it's really, can you find a polynomial time algorithm to something? Because in practice, we never design algorithms which are non-deterministic. They're always deterministic, which means that there's a deterministic Turing machine that kind of can represent that algorithm. And so that means that whenever you have a polynomial time decision procedure algorithm that is solving a particular problem, then that means that that problem is in P, right? So what does it mean then for a problem to be in NP? So the definition is very similar. A decision problem Q is in NP if there exists a non-deterministic, so let's write it out in full, a non-deterministic Turing machine M, which decides Q in polynomial time. Okay, so what does this actually mean, right? Again, we have three keywords. Two are the same as the definition of P, which is to decide Q in polynomial time. The only other thing that NP is sort of allowing, that it's kind of relaxing, is that for a problem to be NP, it can you can provide a decision procedure which is fully deterministic, or which at some point uses non-determinism, right? So you can use non-determinism, right? And so just as a reminder, non-determinism means that you're using some kind of guess plus verify mechanism. So for instance, concretely, that means that in a non-deterministic Turing machine, you might be able to have something like this, where at this point in the Turing machine's transition diagram, suppose you have a bunch of other transitions here, but at this point, the Turing machine has to guess what to do, right? So it makes a guess, and then to verify it, it just keeps on going, right? And if it gets jammed, and if it jams, that means that the guess was incorrect. So it'll backtrack and then it'll try something else. If instead it keeps on going based on the guess and gets to an accept state, that means that it was successful. It doesn't have to check any other guesses, right? Um, and the important thing, right? The important thing is in a non-deterministic Turing machine, if a correct guess exists, then what you should be assuming the non-deterministic Turing machine is doing is it's always getting extremely lucky and getting the right guess, right? So in non-deterministic Turing machines. This is a very important point. Um, the Turing machine M, you should imagine, right? You should imagine that if a correct guess exists, then the Turing machine will essentially find it, right? So if there exists a correct guess, then essentially what's going on in the non-deterministic Turing machine's computation is that it gets extremely lucky every single time where it has to guess, and it makes it to the accept state. If there's no correct guess, then the Turing machine just makes a bunch of guesses, it's wrong, and it just ends, right? And so this is going to make non-deterministic Turing machines, at least at face value, much more powerful than deterministic Turing machines, right? So in practice, right, in practice, we've seen the set of problems or of languages which are decidable. So, from classic formal language theory, we've seen things like AN, BN, CN, we've seen WW, but then we've also seen things like, you can uh, recognize some languages which are really a mapping of, which are really a one-to-one correspondence with some computation. So, for instance, something like AN B power 2n, this is something that you can also design a deterministic Turing machine for. Um, or non-deterministic. It doesn't really matter for the purposes of being decidable. And that means, right, that means that um, when you're talking about P and NP, um, because the definition includes the notion of deciding, then you have P and NP being a subset, a strict subset for that matter, of the set of decidable languages or problems. So, if we just erase this to give ourselves a bit more space, that means that we have the set of problems which are in NP, right? And those are a strict subset of the set of problems that are decidable. It's quite a difficult exercise to actually find a problem which is decidable but not NP. I'll leave it as an exercise. Um, and then within the set of problems that are in NP, you have the set of problems that are in P, right? And so we clearly have that P is a subset of NP, right? So we clearly have that P is a subset of NP. Why? Because a deterministic Turing machine is a non-deterministic Turing machine which doesn't use the guess feature. Right? Same reason for why a DFA is an NFA, which basically just doesn't use non-determinism, right? Same argument for a DPDA, a deterministic pushdown automata, is an NPDA, which essentially just never uses non-determinism, right? What about the other way, right? Because we've seen that there is a correspondence between DFAs and, for instance, NFAs, but this was really in the realm of like what they accept. Then we saw that for DPDAs and NPDAs are strictly more powerful than NPDAs are strictly more powerful than DPDAs, so they don't actually accept the same family of languages. Then for deterministic and non-deterministic Turing machines, it turns out that, if you have a deterministic or a non-deterministic Turing machine, you have the same expressive power in terms of what you can decide, right? So if some problem is decidable with a non-deterministic Turing machine, then it's decidable with a deterministic Turing machine and vice versa, right? The one thing that may or may not be true is um, using a deterministic Turing machine to simulate a non-deterministic Turing machine. causes some kind of exponential blow up, right? So that's the question here about, is NP a subset of P, right? Um, this is the sort of question that remains unresolved of, is P equal to NP? We still don't really know this, right? But it's probably unlikely, right? It's probably unlikely, um, at least to me, because it would mean that you can simulate. So if this were true, then that means that you could simulate the guess plus verify computational paradigm deterministically and still be polynomial in time and still be uh, polynomial in time, i.e., you would still have a decider that's given an input of size n, decides whether that input is a yes answer or a yes instance or a no instance in polynomial time. And we're going to see in upcoming videos, this is probably unlikely because it does seem like non-deterministic gives you an extra edge, which when you go back to the deterministic world, requires you to do some brute force kind of exponential time search. Okay. But that's going to be for the next video. This video was just a sort of introductory a video giving you the conceptual ideas of P and NP. One last thing that I'll say is I think there's a very common misconception that NP means not polynomial because you have N and P, not polynomial in time. This is not true, right? In fact, the definition of NP is that you have some algorithm that works in polynomial time. It's just that that algorithm can use the power of non-determinism, right? And so we'll talk a bit more about that in the next video, though. So thanks for stopping by and see you in the next one.